Hey, fellow mathers! Welcome to the podcast where math is figure-outable. I'm Pam Harris, a former mimicker turned mather.
And I'm Kim Montague, a reasoner who now knows how to share her thinking with others. At Math is Figure-Outable, we are on a mission to improve math teaching.
We know that algorithms are amazing human achievements, but y'all, they are terrible teaching tools because mimicking step-by-step procedures actually traps students into using less sophisticated reasoning than the problems are intended to develop. I made it.
In this podcast, we help you teach mathing, building relationships with your students, and grappling with mathematical relationships.
We invite you to join us to make math more figure-outable. All right. So, Kim, I'm a little excited today because we're going to do something fun.
Am I excited?
I think so. Hold your hats. Okay, y'all. If this is one episode that you maybe don't do while you're driving, this would be maybe one. In fact, pull up a graphing calculator. You could just on your
All
phone.
the people in the car right now are so annoyed because they had this podcast ready.
Yeah, sorry. But yeah, pull up a Desmos, grab your TI, whatever you've got handy. I think we're going to be in Desmos today for some reasons. Here you go. Ready, Kim?
Yeah.
Okay. I'm just going to ask you if you've ever thought about the equation 2x minus 5 equals 4. If you've ever thought about that as the graph of two equations and that equal sign is where they intersect.
I don't think so. Like picturing the two lines.
Well, so if I had the line y equals 2x minus 5.
Yeah.
What do you picture?
So I picture y equals x.
Okay.
And then I think about it's twice as steep.
Uh-huh.
And then it's shifted down 5.
Nice. And then do you have any idea where the line y equals 4 is?
At 4.
And is it horizontal or vertical?
It's horizontal.
Okay, so horizontal line at y equals 4. So if I've got that 2x minus 5, it's sort of steep and it's shifted down, will it intersect the horizontal line y equals 4?
Well, yeah, it'll intersect because it says they're equivalent.
It could be a question. It could be, are they equivalent?
But, didn't you say they were?
Yeah, that's a little tricky.
Okay.
Right. So how many times can two lines intersect, I guess would be a question.
Lines?
Yeah, like we have two lines. We have 2x minus 5 and we have y equals 4. How many times can they intersect?
Once or none.
Or none. Or what if they were parallel?
If they're parallel, none.
Then none. So we could conceivably have equations that could be the same equation. They could represent the same line. That means they would have infinite solutions. We could have equations that intersect once. That means they have one solution. And we could have lines that never intersect, which means they have no solutions.
Yeah.
Do you agree? Okay.
Yeah.
So I'm just going to ask you to type in y equals 2x minus 5. And then I'm going to agree that the way that you described it is what I see on my screen right now. Okay. And then could you graph a second line, y equals 4? And then I'm kind of curious, do they on your screen intersect in one place like you kind of thought they would?
I think hang on.
Do you want to tell us what you're looking at? Or
so I put the first line in, and then in the second entry,
y equals
4.
Not just 4, but y equals 4.
Why didn't I have to do that for the first one?
Well, that's a Desmos question.
Okay.
Okay, so do you now have a horizontal y equals 4 intersecting a what do you call that? Ski wampus. What's diagonal? There we go. Diagonal.
Yeah.
Okay. And can you tell about where? Now, when I say where, this is tricky. Do I mean the x value or do I mean the y value? In this case, I mean the x value. And most often mathematicians, when they say where is a function doing something, they mean the x value. So can you tell the x value of that intersection point?
If I zoom in, I can. Hang on.
Well, you can zoom in, but you can also just put your cursor on top of it and click on the intersection point. And it should pop up.
Lovely.
Did it pop up?
Yeah.
Okay, so is the x value 4.5?
Yeah.
So question, is 2 times 4.5, what is 2 times 4.5?
9.
9. So 9 minus 5 is that 4.
Yep.
Yes. So that makes sense. That is the solution to that equation. Yes?
Yes.
Okay. So often we might look at the equation. Oh, and I wish I was writing something. Where'd my pen go? Okay, there it is. If we were writing the equation 2x minus 5 equals 4, we might say to ourselves, well, something minus 5 equals 4. That something has to be 9. Would you agree?
Mm-hmm.
Okay, so the something is 2x. So now we've kind of got the equation 2x equals 9. So I want to graph that. So on a third, keep the 2 that you have, keep those in there. But on a third line, will you type in y equals 2x? And then on the next line, will you type y equals 9?
Okay.
Now, if you're on the home screen, you're not going to see that y equals 9. It's going to be too high. So
I see it.
Can you drag the whole thing down?
Yeah. I think I've already done that because I see it.
Okay. Where does then, at least for me, it's green. Where does the green y equals 2x intersect the purple y equals 9? And
they're different
again,
for me,
I mean,
but they.
Sorry?
They're different colors for me, but they intersect at 4.5.
Hey, so x is still 4.5.
Uh-huh.
Yeah. So that's interesting. In other words, we can create an equivalent set of equations that has the same solution. And we can create the equivalent set of equations that has the same intersection, at least x value. What are you thinking?
Well, so when you asked me if I had ever thought about the two lines being equivalent, I don't think that I ever thought about those as two independent lines. But what I have thought about a lot is the equivalency between 2x minus 5 being 4 and that being equivalent to 2x equals 9.
Nice.
So like this doesn't surprise me to see it's just another pair of equivalent lines.
So I'm going to be careful about equivalent lines. It's another pair of lines that have the same x coordinate for the intersection. No?
Well, I think there's one pair of parallel lines and a second pair of parallel lines.
Okay.
So yeah, not the first ones you gave me to graph and then the second ones being parallel. I mean like A and C being parallel and B and D being parallel.
Gotcha. Yeah. Okay. Because we shifted them both.
Yeah.
Yeah. Nice.
Okay.
I like that.
All right.
Cool. Okay. So another thing that we could think about would be to graph the line x equals 4.5. So you actually have to type in x equals 4.5. And maybe I should have said, listeners, what will an x line look like? Like we had y equals something was a horizontal line. Now we're typing x equals 4.5. That should be and indeed, it is a vertical line. Yeah.
Yeah.
And then does that vertical line go through those two intersection points that we were looking at? Yeah. So then we could create other sets of, well, we call these systems of equations because they have the same intersection point. Cool. Okay. So the place where I wanted to take this was, we kind of already said a little bit, where if I have a line and another line, they could not intersect at all if they were parallel. They could intersect once, or the equation could be the same. It could be a different way of writing the same line, and then we could have infinite solutions. What if I had a quadratic? So now I'm going to invite you to get rid of all those. We're going to go to base camp. All gone.
Yep.
This time I want you to type in y equals x squared. So that's just the parent function of a quadratic.
How do I make it a square?
Oh,
you can tell I see it.
Caret and then, well, or there. Yeah, you can get it on the keyboard, or you can just do caret too. Okay, so y equals x squared. And I'm going to ask, where does it hit the x-axis?
0.
And that's pretty obvious. It hits that 1 point. So what if I wanted to think about where a parabola hits the x-axis, but I'm going to move that parabola around? How many different solutions might there be with a parabola? And
well,
if I'm
here
asking,
it has one.
Go ahead.
If it's shifted horizontally, it will have either 0. Horizontally, still 1. But if it's shifted vertically, then it could have 0 or it could have 2.
So like, and I'm watching you in the video. So you shifted it up and you said it could have 0 x-intercepts.
Okay.
And if you shift it down, it could have 2.
Right.
So let's go ahead and shift it down. So when you type, keep that same one.
Yep.
And just change it to x squared. So just add on the end of it -4. You might have to
keep the same one.
Yeah, keep the same one. And then did we shift it down?
Yep.
And sure enough, there's 2 x-intercepts. Okay, cool. So a quadratic could have, and we could shift it up. We could do +4, and it would be, and we would have no x-intercepts.
Right.
It can have 1 x-intercept we already saw, and we can shift it down, and it can have 2 x-intercepts. In the one that you have right there, what are the 2 x-intercepts? Can you tell in your graph?
Yeah, -1 and 1.
Kim's squinting. We're both at that age where we have to.
I'm having a hard time with eyes.
We need, yeah, both of us. So did you say -2 and 2?
-1 and 1.
For x squared -4?
Oh, I thought you said -1.
Oh, oops.
So -2 and 2.
There we go. Okay, cool. So then I'm just going to wonder, what about a cubic function? So before you type anything in, listeners, everybody, do we know the behavior of a cubic function? And then do we know enough about it that we could start to reason how many x-intercepts might a cubic have? What are all the possibilities? And then I'll let you play, Kim. We can get rid of the quadratic. So you just want to do x, and I just hit the shift 6 key and then cubed. That's a way to do that.
I think it's going to have 1 or 2.
Can you say why?
Yeah, because, well, if I know what it looks like.
Do you want to type it in before? Well, go ahead and, sorry, I'm making you do 4 things at the same time.
X cubed.
Is that what you thought it did?
Hang on.
While she's typing, listeners, I'll just sort of describe. So a parabola looks kind of like a U, but it's not, the sides aren't parallel, right? They keep getting bigger and bigger as you go to the left to the right. A cubic does not look like a U. How do you even describe the shape of a cubic? It's like funny.
Yeah, it's a weird shape.
So
is there
slope?
I guess what I was picturing when I said 2 is that there is at some point where it is flat, but I guess it makes sense that there's not.
At some point, the slope is
it?
It's 0. It's not.
But at a single point.
Say that again.
Like at a single point.
So at the origin, y equals x cubed is 0.
But it makes sense that it would only have 1 then.
Okay, but then we can tweak a cubic by adding a quadratic to it or subtracting. So just to the one that you have, do -2x squared. So you should have x cubed minus 2x squared. And now we get a different look of a cubic. So it's still a cubic in the long run, but we
That's what I drew in my paper. Yeah,
that's what you had. So you had a form of a cubic.
Yeah.
And so I think that's why you said there could be 2. So if listeners, if you graph x cubed minus 2x squared, we've got a 0 at 0. It's still going through the origin, but we also have a 0 over there at 2. Yes?
Yep.
Cool. So when we did a quadratic, we said there could be a possibility that there were no x-intercepts. Is that possible with a cubic?
No.
You're shaking your head no. Why?
No. Because it always is going to cross the x-axis at one of the 2 points.
That's part of the end behavior of a cubic.
Yeah.
That's the definition of a cubic is as we go to the left, it's getting more and more negative. As we go to the right, it's getting more and more positive. Somewhere it's going to cross the x-axis at least once, but it might only be once. Okay. Then you said twice. Hey, and we're looking at an example of twice. Mm-hmm. So it's sort of bumping the x-axis at the origin. The x cubed minus 2x squared is sort of bouncing there.
Yeah.
And that's a double root. And then over there at 2, we have a single root. So at 2. Okay, cool. Is that it? So it will for sure have 1 x-intercept. It could have 2 x-intercepts. Can it have more than 2?
I don't think I know enough about the transformations to know if something causes it to go back down.
To dip again?
Yeah.
Yeah. So look how we just set Kim loose. Now she could start to play. How could she mess with a cubic? So what are all the ways you can mess with a cubic? Well, that's interesting. We just subtracted a quadratic. You can add a line, you can add a constant function, subtract or add a line or a constant function, and we would then let kids play with that and then say to them, what is the long run behavior of a cubic? And then what are the different kinds of short run behaviors that we could do? So Kim, I'm just going to invite you to take that one that we had and just add one.
Yeah, I don't think, go ahead. You said add one.
Yeah, add one. So you should have x cubed minus 2x squared plus 1. And now how many x-intercepts do we have? Now we have 3. So we know that it's going to at least have 1. It could have 2. We are seeing 3. I think we let the listeners go play. Could we have 4 with a cubic? How can you? And y'all, you could just start typing stuff in. Now, what's the definition of a cubic? Well, definition of the cubic is it's a polynomial where the term of highest degree is 3. I didn't just say that well. The highest degree, the term with the highest degree is no higher than 3. It has to have a 3. If the highest degree term is 3, then it's a cubic. And It can't have other, it has to be polynomial.
Right.
So then let kids play with that. And then I'm just going to expand that. If we get kids good at the parent functions, what is the behavior of an exponential function? And like Kim just very nicely said, what are all the possible transformations?
Right.
How about a logarithmic function? How about a sinusoidal function? Like if we could get kids to actually know that behavior, then they have a sense of the possible numbers of zeros, which means they are solutions to equations, which means they are intersecting the graph, though they're x-intercepts. So solutions are connected to zeros of a function, are connected to x-intercepts of a graph. All of those can be informed by the sense and feel that we have for parent functions. All right, there was our quick little fun that we had today.
Yeah, so I feel like different than other problem strings, this one is about helping kids name what is happening to the graph as you add the next problem. Like what shift is happening, what move is happening in order to give them more experiences. So you would probably come back then with another string and they might have a little bit more of experience with now students who didn't know what a cubic looked like. They're like, oh yeah, I remember the shape of that. And now I may or may not remember that it can have 1, 2, or 3 intersections with the x-axis, but you're layering on more of that feel for what it can and can't do.
Nicely said.
Yeah.
And I'll add one other just quick thing. And we're using technology as a tool to understand what's happening, not as a crutch just to get answers. If we could do more of that. All right, y'all.
Yeah.
Thanks for tuning in and teaching more and more real math. To find out more about the Math is Figureoutable movement, visit mathisfigureoutable.com. Let's keep spreading the word that math is figureoutable.